today we'll talk about disjoint sets. Or sometimes it's called union-find data structure. Sometimes it's also called merge-find, but it's quite rarely. So usually it's called disjoint sets or union-find. So it's another special data structure. It looks pretty strange, but it's surprisingly important in many algorithms which we will discuss later in this course, mostly in the next year, because we will discuss graph algorithms in the third semester, so it will be in the next year. But maybe we'll use it in some another algorithms in the next semesters also. Mostly in this semester we'll learn some data structure, some base, and later we will use this data structure to make some efficient algorithms. So what is disjoint sets? It's a very simple data structure. It maintains the set of some objects. Let's say, for simplicity, that we have some n objects. Let's say 1, 2, 3, 4, 5, 6, 7. Good enough. So we have some 7 objects, and these objects are grouped into some sets. So each object belongs to exactly one set. So we have some number of disjoint sets. So that's why it's called disjoint sets. So for example, here we have like set of these 3 elements, these 2 elements, and these 2 elements. Cool. So it's just like we divide all elements into some sets in some principle. No, we have no summertime in Russia. It was deprecated a few years ago. Sorry. I have a Google Calendar. If you're afraid you may forget about it, I have a Google Calendar of my Twitch streams, so you may just copy this calendar into your calendar to make sure you will not forget about future lectures. What I was talking about? Disjoint set. So we have some objects. These objects you can download this calendar from the Twitch description. It is somewhere in the bottom of the Twitch dashboard. So here, so we have some elements. They are divided into some sets. So what we want to do with these sets? We want to perform 2 types of operations. Basically, it's union and find. Why the second name of this structure is union find. First operation is union. Union is bad word for programming, because union is a reserved word for C++, so you can't make a function named union. So I usually call it something like unite or join or something like that. So. But here I will write union because I'm not writing in C++. So what this function does, it gets 2 arguments. We have arguments x and y. And it simply unite these 2 sets. So we take the set that contains element x. Let's say this element x. We take the set which contains element y, and we just unite these 2 sets into one big set. So we have these 2 sets, so we make one big set like this. That's the first operation. We just take these two sets and make one big set out of them. And the second operation is to find the set which contains element x. It's usually called find. I usually write get because I know for historical reasons I think. Well, let's make it more simple. Let's say find x. So this function returns the set which contains element x. That's all. We have these two operations. First operation is just unite two given sets into one, and the second operation is return the set which contains the given element. That's simple. That's all. Now, in the second operation, we need to return the set which contains the element. So we need another class of objects which represents the sets. Yeah. So we have the elements and also we have the sets of elements. So we need like two types of objects. That's not very comfortable to have two types of objects. So to make it more simple, we will do the following. Instead of returning the set which contains the given element, we will return one special element of this set. So for each set, is this. For each set, we will mark one element and say that this particular element is the representative of this set. So for each set, one element is special. Let's say this element, like this element, and this element. So these three elements are special elements. So and each set contains exactly one special element. This element is representative of this set. And now instead of returning this special objects of set, we will return this representative of this set. For example, here if we call find from element, let's say 6, it will return 3. And if you call find of element and say 5, it will return 5. So element 6 belongs to this set. In this set, 3 is a representative element, so we will return 3. And element 5 belongs to this set. 5 is a representative of this set, so we will return 5. Important thing that representative always return the same element. So if you call find from two elements of the same set, you will get the same element each time. So if you call like find from element 2, it will return the same element 5. So this is how you may understand that two elements belong to the same set. So if you want to check if two elements belong to the same set, you call find from both these elements and check that this find returns the same representative element. Cool? You're too quiet today, so let's write something in the chat. Like, so I understand everything is clear by now. That's all. We have these two operations. Yeah, like this. Cool. Now, let's discuss some very simple way to implement disjoint sets. Okay. First implementation, very simple. Let's just make array. Let's make array P. And element in array P will be the representative of element X. So each element of array, we have 7 elements. No, too many. 7, right? Oh. So we make array of size n, and for each element of the array, we will maintain the representative of the set which contains element x. For element 1, the representative is 5. For element 2, it's 5. For 3, it's 3. For 4, it's 7. 5. 3 and 7. That's all. Now let's implement these two functions. Let's have this function find. So how to find the representative of element x? No, it's quite simple. We just have the array of all representative of all elements. So we just look in this array, find the representative, and return this representative. It's very simple. That's all. Now, how to unite two sets into one? So let's see, union of x and y. First, let's get a representative of these two sets. So let's say x is the representative of the set x, and y is the representative of set y. Now, what we need to do, for example, we have these two sets, this x, this is y. So what we need to do is just take all elements of one set. No, we need to choose what element will be the representative of this big set. For example, let's say that element y will be the representative of this union of two sets. So we need to take this big set and set the representative of all elements in the set to y. For these elements, it's already y, but for these elements, we need to set the representative from x to y. So we need to find all elements which representative is element x and change it to y. So just iterate all elements. It's from 1 in our case. It's quite uncommon to have indices from 1, but okay. We started from 1, so let's keep it. It's from 1 to n, and say if representative of I equal to x, then set representative to y. That's all. So it's very simple realization of this idea. Now, let's calculate time complexity. What is the time complexity? No, for find it's obviously constant. Another one. It's constant. And for union, it's obviously linear because we have this cycle, so we always make n iterations of this cycle. So it's big O of n. Yes, we will definitely prove it later. Yeah, that's just the first version. Okay, that's the simplest implementation of the disjoint set. It's quite bad because union takes linear time. We don't want to spend linear time. Now, let's stop here for a little. Let's talk about how many union operations can we perform in our data structure. How fine is constant? Well, we just look in the array and array lookup take constant. It's not a hash map. It's not even a hash map. It's just an array. So we have very fast operation find, but very slow operation union. Let's go back. So what I want to talk about is what is the number of union operation can be in your algorithm. Since we only unite these sets into big ones, the number of union operation cannot be more than n-1. So we cannot have more than n-1 operations. Well, that's basically because in the beginning we have n sets, and each union operation decreases the number of sets. Yeah, so we have one set instead of two sets. So we decrease in the number of sets. So in total we'll have no more than n-1 unite operations. So now, later, in data structures like this, then you know the total lifetime of your data structure. Like if you know that the number of operations is constant, so you start with these sets and you only make n operations until you reach the final state of the data structure. You usually calculate not the single time of operation, but the total time of all operations. So instead of calculating the time of single operation, we will usually calculate the total time of all unit operations. That's more like amortized time. It's like the basic case of the amortized time. When you calculate the amortized time, you like divide the total time by the number of operations. But here you know the number of operations is already is constant. It's always will be n. So if you just calculate the total number of operations divided by n, you will get the amortized time. In this case, the total time of all union operations will be total will be n squared. That's all. That's all about this simple implementation. Now let's move to the something more complicated. First optimization. Let's see what we're doing here. Here we just iterate over all elements which belong to one set and like move these elements to another set. So we need to find all elements in array P equal to X and change it to Y. So is it possible to iterate over all elements with a given value faster than just look on all elements? So can we just, like in this array, we need to find elements with X equal to, let's say, 3. So we need to find these two elements and change these two values to 7, right? So let's try to find these two elements without scanning the whole array. So how can we do this? Quite easily. We can just maintain the list of all elements for each value X. So for each representative, let's keep the list of elements which belongs to corresponding set. So 1, 2, 3. I don't have them. I only have representative 3, 5, and 7. Let's have representative 3, 5, and 7. So for 3 we have elements 3 and 6. For 5 we have elements 1, 2, and 5. This list shouldn't be sorted. So we have, like, for example, 2, 5, and 1. And for 7 we have 7 and 4. And we also have empty lists for 1, 2, 3, 4, 5, 6. So let's maintain n lists. For each element X, we will maintain the list of all indices such that the value equal to X. Let's go back here, let's go here. So how can we rewrite this union? Let's say X will find X, Y equal to find Y. Now we need to take all elements with value equal to X. To do this, we just take the corresponding list. We take this list and iterate over these elements. So we take these elements, go in array P and change these values to Y. Let's call this lists. So we take list of element for value X. So again, what is the change? Here, instead of iterating over all elements, we iterate only over elements with value equal to X. So we don't need to make this check. We only iterate over elements with value equal to X. And just change this value to y. That's all. And we also need to fix the list. We also need to transfer these elements from these lists to these lists. So this is x, this is y. So we need to iterate all these elements, change the representative to y, and move these elements to this list. We also can clear this list and then just for simplicity. Just to free some memory. It's not important, but just. Okay. That's all. Now, did we change something in the time complexity? Let's think. The find still works the same. So the find function is still the same. So we just return the value from array P. So it still works in constant time. What about the union? Did we actually change the total time for this operation? No, it obviously can work in linear time. So in the worst situation, when, for example, we have one big set of elements, so we will iterate over all elements. Here we will iterate over all elements of some big set. So the number of elements in this set can be linear. So this time, the number of iterations of this cycle may be linear. Delete modify? Not sure what you mean. No, we never remove elements from the set and we never modify anything. We make two simple operations. We may unite two sets and check which set belongs to given element. Maybe I don't get your question. Let's go back. So, what is a multi? Yeah, no. So let's go back here again. Let's think. This union function obviously may work in linear time. In the worst case, this function may work in linear time. But what is the total time? Is it possible that the total time is still n square? So, is there a situation when this procedure is called n times and the total time complexity of all these n calls is still about n square? Okay, just let you think a little while I'm erasing this. Okay, the answer is it is possible. Sometimes, if you call this union function in wrong order, you may get a quadratic number of operations. For example, if you have n elements, and in the first union operation, you unite these two elements. So the first union, let's see. So you call union from 1 and 2. So you unite these two elements and you spend like one operation. So you need to change again. So array P looks like this. So you called union for elements 1 and 2, and you need to change the representative from 1 to 2. So you change this 1 to 2, and it costs you 1 operation. And now you call union for elements 2 and 3, for example. So you need to change the representative elements from 2 to 3. So you change these 2 into 3. 1 and 2. 3 and 3. And it costs you 2 operations. And now you make union of 3 and 4 and so on. You need to change these 3 elements to 4s. And it costs you 3 operations, and so on. So the total number of all operations will be about n squared. Is it clear enough? So we have this sum. The first operation costs you 1 operation, then it costs you a second operation costs you 2 operations, and so on. So the sum of these times will be something like n multiplied by n minus 1 divided by 2, something like that. Yeah? So it is big omega of n squared. Yep. So it's not actually better than we have it here. So we still have n squared time complexity here. That's kind of sad. We tried to improve everything, but we have the same time complexity. But the good thing is that we actually can improve this by using the simple trick. Let's look here. When you unite two sets, you have set containing x and set containing y. You may choose which elements, which element will be x and which element will be y. So we have two sets, set x and set y. You may transfer all elements from x to y. So you may find all elements with representative equal to x and change it to y. Or alternatively, you can find all elements in this set and set representative to x. So you can move all elements from here to here, or you can move all elements from here to here. Let's look on the size of these two sets. And let's make the x the smallest of these two sets. So let's look on size of these lists, for example. And if x is the biggest of these two sets, we just swap them. So let's say if lists of x size is bigger than lists of y size, we just swap them. And now x is always the smaller of the sets. So we always take the smallest set and transfer the elements to the bigger set. That's the whole trick. Quite easy, right? Now let's think, did we actually change something? Did we actually change something? Let's look on the total time complexity again. Now, this situation like here will not happen. Because, for example, if you unite elements 1 and 2, what will happen? Again, you have array P, you have 1, 2, 3, 4, 5, 6, and so on. You make union of elements 1 and 2. So again, you check which set is smaller and move elements from 1 to 2. So you change this 1 to 2. And now you make union of 2 and 3. But you see that the set of element 3 have size 1. And set of element 2 have size 2. So instead of moving these elements from set 2 to set 3, you move one element from set 3 to set 2 back. So you change this 3 to 2. So it's already cost you one operation. Now again, you try to unite 3 and 4, so you unite these two sets. You have 3 elements here, only 1 element here. So it's faster to move this 1 element to this set. So you change this to 2, and again cost you 1 operation. So the total number of all operations will be linear. Yeah. The worst case, as you rightly mentioned, the worst case is when we merge two sets of equal size. So when we have two sets of equal size, then we need to go from one big set and transfer all elements to another big set. This may happen. But let's think about the worst possible case. What is the worst possible case? Worst possible case is when you always merge two sets of equal size. What will be the total time complexity? What will be the total time complexity? Let's look on some element. Imagine you have one element. You have some element x. Let's look on the lifetime of this element. Let's see how many times can we move this element from one set to another set. So in the beginning we have element x in the set of itself. So we have a set of size 1. Next time, when we will move the element to another set, is when we will unite this set with another set. So we have another set of size at least 1. So we will combine these sets into one. You have sets of size at least 2. Yeah? Yes, and square over 2 is the same as in square. Yeah. No, it's time complexity. Here we just get rid of all constants. So yeah. Yeah, time complexity of one operation, yes. Time complexity of one operation is still linear. I am talking about this total time complexity. Here, yeah, the time complexity of one operation in the worst case will be linear. So if we merge two sets of size n over 2, so we have one big set, another big set, we have n over 2 elements here, n over 2 elements here. Yeah. So in the worst case, we need to transfer all these elements to this set. So we take n over 2 operations. So it's still linear. So worst time complexity for one operation is still linear. That's right. But I'm talking about total time complexity. So I want to calculate the total number of operations in all union operations. And last time, the total time was n squared. And I claim that now it's smaller. It's now, if we use this trick, the total number of operations of all union operation will be smaller than n squared. So let's go back there. Let's try to calculate the total number of all moves. So in a single operation here, what caused the time complexity? It caused these loops. In each loop, we just move. See, this is one move operation. Let's calculate the total number of moves of all elements during the lifetime of this data structure. So we start from elements of sets of size 1. So each element belongs to a special set containing only this element. And each time we unite two sets into one big set. So in total we have n-1 union operations. I want to calculate the total time complexity of these n-1 union operations. And I claim that it is smaller than n squared. Because this. Why it's smaller than n squared? Let's look on some element. Let's look on element x. Let's see how many times we can move this element here. So for each element x, let's calculate the number of times we move this operation. So we change the representative for element x. So how many times? Many times this p of x changes. So if you calculate this, we will calculate total time complexity. Because this total time complexity is summed from this part. And in this part, we just move element from one set to another. So we change the representative for this element. If we calculate the total number of times we change the representative for the given element, we will calculate total time complexity. Clear enough? So let's go back. So we have element x. In the beginning, we have the set of one element x. Now, each time we move the element x is moved to some set with bigger size. So first, we have element x in a small set of size 1. Next time we merge this element x of some another set. So we have element x in some set of size at least 2. Next time, when we will move element x, it means that element x belongs to some set which is smaller of these two sets. So when we will move this element x next, we will merge these two sets in some another set of size at least 2. So element x will belong to some set of size at least 4. And so on. Next time, when we will move element x, it means that element x belongs to smaller of these two sets. So it means that we unite our set with some another set with size at least 4. So we have some another set of size at least 4. We make another union. So the size of this set is at least 8. And so on. After each union which causes the element x to move to another set, the size of the set which contains element x is increased at least twice. So the total number of times when we move element x from one set to another is at most logarithm of n. And that is true for each element. So each element of our data structure is moved from one set to another at most logarithm of n times. So the total number of moves is the same as time complexity. Is big O of n log n. Let's mark it here. Clear enough? Again, you are too quiet today. Just say something from time to time. That's all. And this is actually quite important technique, especially so most of you come from school forces, so you learn some competitive programming. It's quite important technique when you need to make some mergeable data structure. So if you have some data structure and you can like insert elements one by one, and you want to make mergeable data structure, so you want to be able to merge two data structures into one. So the easiest technique to do this is just to take a smaller data structure and put elements one by one in the bigger data structure. And if you do this, the total number of moves of elements from one data structure to another data structure will be n log n. And you can see this in some task when, for example, you have some tree and you need to calculate something on this tree. So for each, you may take data structure from you need to unite all children into some big data structure. You have data structure for each child of the given node, and you need to merge these data structures into one. So you can do it by taking the biggest of the data structures and just moving all elements from other data structures to this bigger data structure. And if you do this, if you always move elements from small data structure to big data structure, the total number of moves will be n log n. For example, if you have a binary heap, yeah, like we discussed on the second lecture, I think, binary heap, and you want to be able to merge two binary heaps. you can just copy all elements from small binary heap to the big binary heap. So in total, you will have n log n moves from one heap to another heap, and you can move element from one heap to another in logarithm time. So total time complexity will be n log square, something like that. Yes, we'll talk about minimum spanning tree next year. But yes, we have this in the plan. It's a long course. We'll discuss many data structures before. Okay. Cool. Now the final part. Now we'll finally build the cool data structure. So this all is a very important basic, actually. So if you, again, this technique, like discussed here is very important when you need some mergeable data structure. If you have some data structure which you can move elements one by one, you can make mergeable data structure with total cost like n log n. Now I will erase everything and just rewrite it from scratch. Okay. One final part. Now we'll discuss actually how to make this data structure faster than n logarithm time. The idea is to get rid of this logarithm. So logarithm is pretty small function, but still quite big. So we will make another data structure which do the same operations, but works faster than in logarithm time. Let's go. So what will be the idea? Okay. Yeah? Oh, cool. What is the idea? Again, let's have some sets. 1, 2, 3, 4, 5, 6, 7, 8. So we have some sets like here, here, and here. So we have some sets of elements. In each set we have one special element, representative element. So we have representative, representative, and representative. We will maintain these sets as trees. For each tree, the root element of the tree will be the representative of the set. For example, for this set 1, 2, 4, we may have 3 like this. 2, let's have 1 here and 4 here. So this tree represents this set. The root element is the representative, and all elements have links to the parent of this element in the tree. For this set, for example, we may have something more interesting. We have different tree. We may have like 3, and here we have 5, and here we have 6. We may have 3 like this. So this tree represents this set. Again, element 3 is the root of the tree, and each element have a link to the parent element in the tree. And here we have 8 and 7. Let's have 8 and 7. That's all. That's how you represent these sets. How to implement this? Very easily. To implement this, we only need to have links from each element to the parent element. So again, we need only one array. In this array, we will maintain the pointers from element to the parent element. So we have array P. P of x is the parent of element x. Well, for example, here what we have, element P.
and 4, it's 2, and here it's 2. For 5 it's 3. For 6 it's 5. For 7 it's 8.
What should we write as a parent element for the roots of these trees? It depends on your implementation. You may write something special, some special here like -1, but actually it's easier to write the pointer to itself. So it's easier to make pointer to itself here. If you do it like this, the code will be simpler. Just we'll write the code later. I believe the whole code will be here. It's that simple. So it will be 2, 3, and 8 here. Go. Next. Now, let's implement two operations we need. So we need operations find and union. Let's start with operation, let's say find. So how to find the representative of the set? So we start from element x, and we go to the root of the tree using this link. So we go from element x to its parent, then to its parent, and so on until we reach the root of the tree. Well, let's do it like this. Let's say if... Do you want to make it recursively or non-recursively? Let's make it non-recursively. So let's say while parent of x is not equal to x, like move to the parent. Like this. Good enough. So we start from element and go to the parent until we reach the element whose parent equal to x. And this element will be the root of the tree, because only root have pointer to itself. So we go to the root and then stop and return x. Cool. How to make union? Well, first, again, let's move to the representative of both elements. So x equal to find of x and y equal to find of y. Now we move to two root elements. So we have x here and y here. And now we need to combine two trees into one. And the simplest way to do this is just to make pointer from one root to another root. So we'll just move this pointer from x to y. So here, this pointer, we just move it to here. That's all. Now, if you start to find the root element from any element in this tree, you follow these links and you go to element x, then use this link and go to element y. So from each element in this set, you will go to element y, and from each element in this set, you will go to element y. So y is the representative for all elements in this big tree. In find, we have pointer to the node. Usually you just have the array, so all elements are just enumerated with integers from 1 to n, something like that. So usually they are just enumerated by integers small. You can do this in pointer machine, I believe. Yes, I don't see any problems. You can do it in pointer machines. Yes. But here I just assume I have an array. But I believe you can do the same in the pointer machine. Yes, we don't need any special from arrays. Yes, we can use just the elements and pointers. Yeah. It's not balanced. That's correct. That's correct. We'll get to it a little bit later. By now, in this implementation, let's calculate time complexity. First of all, the time complexity of this union is composed of these two finds. So the complexity of this is same as for find operation. And here you have like constant number of here. So the union is pretty fast. So the only thing we need to optimize is operation find. Yeah? The operation find may be slow, but go a bit later. But union makes some two finds and then constant number of operations. Let's go to find. What is the time complexity of the find? It depends. So we start from some element and use this link to move to the root. Is it possible that the number of these jumps will be linear? No, it actually can be. It can be linear. So if you merge these two trees in the wrong order, like we did it before. So if you start from element 1 and merge it to element 2, then merge this tree with element 3, and then merge this tree with element 4, you will have this bamboo tree. So you start from, so this tree becomes some one big path. And in the end, if you call find from this node, you will need to follow all these links up to the last element. So in the worst case, this find may work in linear time. That's not good. All this lecture we try to avoid this situation. So how to avoid this situation here? So is it possible to make this find work faster? And quick answer is yes. And there are two different strategies how to improve the time complexity of this find operation. First idea, let's try to avoid situations like this. So let's try to avoid these long paths. And to avoid situations, we need to kind of make the tree balanced. How to make the tree balanced? There are different strategies. Simple explanation is what you usually need is, again, like in previous implementation, you need to link the small tree to the big tree. So if you have two trees of different size, you need somehow to pick the small tree and connect it to the big tree. I will use the rank heuristics, but you can. There are several different heuristics which works as well. So I will use the rank heuristics. So what is the rank heuristics? Heuristics, I think. Let's maintain for each element its rank. Rank is basically the maximal possible distance to the leaf in this node. So we have for each element x, we find the longest path in this tree, and the length of this path will be the rank of element x. Now, for example, here we have element 2 have rank equal to 1. These elements have rank 0. These have rank 0, it's rank 1. And this element 3 have rank equal to 2, right? So here we have rank 2, here we have rank 1, here we have rank 0, rank 1, rank 0, and so on. So each element has the rank which is equal to the length, like this is called the height of the tree. So it's the maximal possible distance in this tree. Good. And now what we will do, we will try to connect tree with small rank to tree with the bigger rank. So here, Let's say x will be the element with smaller rank. So if rank of x is bigger than rank of y, then we just swap them. And then connect x to y. And now we need to recalculate the ranks. How to recalculate the ranks? Oh, if you connect two trees. If you have two strings of different ranks, so if rank of x is smaller than rank of y, and you connect it like here. So you have some path here, some path here. What will be the longer path in this big tree? Let's see. So here, this path will have length rank of x plus 1, and this path will have length rank of y. And if rank of x is less than rank of y, they're integers. So rank of x plus 1 will be less or equal, let's write it here, the rank of y. So the maximal rank, or the maximal length of this path will be just rank of y. Yeah, rank is the distance to the to the farthest leaf in this one. So. Sorry. Yeah, that's correct. We need to find the maximal distance in this tree. Again, if you merge two trees of different ranks, then rank of x plus 1 will be less or equal than rank of y. So the maximal possible distance will be still rank of y. So this will be no greater than this. And if you merge two trees of the same rank, then the maximal path will be rank of x plus 1. So the rank of the y will be increased by 1. If you have the same distances here, then the maximal distance will be this. So rank will be increased by 1. Yeah, it's the same at the height of the tree. If you know what is the height of the tree, it's absolutely the same. Like here. Here are the ranks of all nodes. So if ranks are equal, we need to increase rank of y by 1. Yeah. Good enough. Good enough. That's the whole heuristic. So that's the whole trick. That's all. Now, I claim that these heuristics will cause this find operation works in logarithm time. So I claim if you do it like this, then the maximal distance you can travel here is logarithm of n. Why it is true? No, let's see. Let's see. If you have element of rank r, so you have some tree. Yeah. I claim that the number of elements in this tree is at least 2 in the power of rank of x. Like here, you have element of rank 2. It means that this tree contains at least 4 elements. So at least 4 elements. for example, this length y, this tree contains at least 2 elements. So it contains at least 2 elements, and so on. Optimal number of children. No, you want to have maximal number of children. So it's never bad to have many children, because if you have many children, it means that the depth of tree is smaller. So you always go up to the roots. You never go down. So the big number of children is not a problem. Yeah. Again, let's go back. What I want to prove? I want to prove that the rank is never more than logarithm of n. That's what I want to prove. How to prove this? Very easily. Let's look on element x. Let's prove that the number of elements in this tree is at least 2 in power of rank of x. Why is it true? Well, because by construction. So what happened here? When you combine 2 trees of different ranks, then rank of y will be the same, and the number of elements will be more than before. So we increase the number of elements, and the rank is the same. So this property is still satisfied. And when you merge 2 trees of the same rank, then you have like no less than 2 in power of r elements here, and no more than 2 elements of r here. So total number of elements will be at least 2 in power of r plus 1. So when you combine 2 trees of the same rank, the total number of elements will be at least 2 in power of r plus 1. And you increase the rank by 1. So if before this union you have 2 trees of size at least 2 in power of r, then in the end you have big tree of rank r plus 1, and the total number of elements is at least 2 in power of r plus 1. So if the property is satisfied before the union, it is satisfied after the union. And in the beginning of the structure we have all elements, we have single elements of rank 0, and element of rank 0, the size of this tree is 1, so it's 2 in power of 0, it's satisfied. So this property is satisfied in the beginning of the structure, and it is satisfied after any union operation. So this union operation do not break this property. So in each moment of lifetime of the data structure, for each element x, the size of this tree is at least 2 in power of rank of x. And if it's not proper for x, and this is no more than n, it means that rank of x is no more than logarithm of n. That's all. In the next semester we'll talk about balanced trees. That's actually what happens usually in balanced trees. So when you have balanced trees, you will have usually some proofs like this. So instead, when you want to prove that something is up to logarithm, you make the inverse situation and prove that this part is up to exponential of this. Something like that sounds. Okay. So that was the first heuristics. You just maintain the ranks of all elements and link this tree with small rank to the tree with big rank. And if you do this, you keep your tree balanced, so the ranks of all elements are up to logarithm. So here, when you make find, you follow to the root, and the length of this path will be no more than logarithm. That's all. That's the first basic heuristics, how to maintain this tree balanced. Cool. Second heuristics is very, very different. What we can do, we can improve this find function. This technique is called path compressing. What does basically mean? Imagine you have this find, you call this find operation, and it takes long time, so you have some very long trips to the root. So you call find from here, and you need to follow all this route to the root element. What you can do? You can improve your tree for future calls. So when you call this find in the same element next time, you already know that you will end up in this element. So what you can do is you might change your pointer to the parent element to the root element. So you might change this pointer to here. So next time when you will call the find from this node X, you will go strictly to the root element. So the next call will be working in constant time. And also you may do the same for all elements in this root. So for each element in this path, you can change the pointer from the current one to the root. So you may change all pointers. This already to end. To the root element, like this. That's called path compressing. So again, what is the difference? Every time you call the find, you follow this route to the root element, and when you go back, you change all the pointers to the root element instead of the parent element. That's all. That's the whole idea. So let's modify this find. Let's move it here. Do you want to make it recursive or non-recursive? That's a matter of taste, actually. Let's make it non-recursive, just for to make it interesting. So again, we follow to the root. Now we have x to the root. We need to remember. So let's move to the root. Let's make y here. So it's y equal to x while p of y not equal to y equal to p of y. So we move to the root and then move again and change all pointers to the root. Let's do it like here. While p of x not equal to x. So I want to move here and change the pointer. Say z equal to p of x, p of x equal to y, and then x equal to z. It's overcomplicated, but okay, good enough. It's much easier when you write it recursively. When you write it recursively, you just call a recursive function for the parent. The recursive function will build everything here. So in the end, you just go back from the recursion and change your pointer to the root. So it's like two lines of code. But this still works. Okay, question's not for me. Okay, that's all. So what is the idea? Again, what is the idea? Every time you call the find, you not only find the root node, but you also change all the pointers on this path to the root node. So next calls of the find will work in constant time. So if you after this operation you again call the find from any of these nodes, you will go directly to this root node. So each next call will cost you constant time. That's the idea. Okay. Now the results. So what will happen if you use this technique? If you use this technique without the rank heuristics, if you use path compression, and without any other heuristics, you just use something like this and connect any trees in any order. So you may have these long bamboo trees, but you always make path compression. So these heuristics alone will give you logarithm time for the find operation. So the amortized time of this find will be log n. And the more interesting fact is that if you use both heuristics, so if you use path compression and some other heuristics which maintain your tree balanced, so if you use path compression on some balanced tree, like we did when we have like rank heuristics. So if you, for example, use path compression plus rank heuristics, the time will be even less than logarithm. So the amortized time of the find will be actually big O of inverse Ackermann function of m and n. So what is this? This quite interesting function. So it's called an inverse Ackermann function. Here you have two arguments. So n is the size of the tree. It's the number of elements in our sets. If you may think about it in terms of sets or in terms of trees. It's no big deal. And m is the number of operations. Number of calls of find this function, of finds. So if you call this find operation m times in total, then time complexity will be something like that. And the interesting about this function is that if n is increasing, that function will be also increasing. And if m is increasing, so if you increase the number of calls, this function is actually decreasing. So it becomes smaller. That actually makes sense. So if you have some structure of your tree and you make a lot of find operations, then the more operations you make, the shorter the paths became. So after each find operation, the tree is kind of improved. So this length became shorter and shorter. So if you make many find operations, the tree became something like that. So all operations, all future find operations will cost you constant time. That's interesting. So this time complexity actually depends on number of operations you make on this data structure. If you make more operations, they actually work faster than if you have small number of operations. That's interesting. We will not talk about this function today. I'm always planning to have a special lecture about this, but I never have enough time. that's interesting. So we may have special lecture about it at some point, but the problem is you need to spend like an hour to explain what the function means. It's maybe not an hour, but like 30 minutes just to explain what is the inverse Ackermann function. It's kind of complicated. So instead of this, we will prove some more simple upper bound on this time complexity. We will prove like the worst case for this situation. In the worst case, m equal to n. So if m equal to n, then this inverse Ackermann function became the iterated logarithm. And we will prove this upper bound. What is the iterated logarithm? The iterated logarithm is a very simple function actually. It's mostly how many times you need to get logarithm of this integer until it becomes small. So let's look on some integer 2 in power, let's say 65536. Let's take logarithm of this element. So we take logarithm of this number. You have 2 in the power of 16. Then again, you take logarithm of this number. You have 16 in the power of 4. Then again, you take logarithm, take 2 in the power of 2. Then you take logarithm of 2 in the power of 1, 2 in the power of 0. Now, let's calculate the number of times we take logarithm until we have small number. For example, here we start from this number, take logarithm until we are here. So we take logarithm like 5 times. So iterated logarithm is the number of times you take logarithm of the number until it becomes small enough. Let's say here is small enough. So let's say that iterated logarithm of n of this number is 5. Sometimes it's plus or minus 1, so it depends on where you want to end. So if you end here, then it's 5. If you want to make one more step, then it will be 6. It's not a big deal. Okay. So this is the iterated logarithm function. It is very slow. It grows very slowly. So even for this big number, it's up to 5. So it's extremely slow. Well, actually, if you have these many elements in your data structure, then you have much more interesting problems. For example, you don't know how to store these elements because there is not enough atoms in the universe to store these elements. So you usually don't have these many elements in your data structure. That's what I want to say. At least by now. Maybe physicists will learn something about how to store this number of elements in the future computers, but in normal computers by now, which you have no chance to have this big data structure. That's all. Now, what I want to prove? I want to prove that the time complexity of find operation, amortized time complexity, is big O of iterated logarithm of n. That's what we'll prove right now. That's not that fun as this upper bound, because this is much more interesting. But it's good enough. So we will prove that the time complexity is pretty small. Cool. So let's go. How to prove this? To prove this, again, this is the amortized cost. So to prove the amortized cost, we need to calculate the sum of time complexities of all find functions. So we have this tree, and we call the find operation several times. So again, you have situations like this. So you start from the structure, and you call the union, then you call find, you call another find, union, and so on. So you make some number of operations, like M operations. And I want to calculate the total time complexity of these operations. And then I will divide by M and get the time complexity one operation. Let's go. So, how to calculate the time complexity? Let's look what happens when you perform the find operation. So you have some element x. You move from here to the root. So the time complexity is equal to the number of these jumps. So you start from element x and then move to the parent until you reach the root of the tree. So the time complexity is formed by this, by the length of this path. So what we'll calculate? We'll calculate the total length of all these paths. Yeah? Okay. First, let's look on this last edge. So this last edge is special. Let's calculate these edges first. We have one last edge in each find operation. So the total number of these last edges will be m. So let's just calculate these last edges separately. So total time will be no more. Let's go. So in each find operation, we have one last edge. So let's calculate it separately. So this will be the last nodes, last edges. Nice. Now let's calculate these edges. To calculate these edges, we will split all edges into two groups. We will have how to call them? I don't know. I don't know the correct terms in English. It's interesting. Let's call them small jumps and big jumps. No, I want to. Yeah, that's not a big deal. Even if the term is not correct, it's used only in this proof. So, as soon as the proof is correct, it's fine. Okay, let's look on some node x. So you have this node x. Let's look on this edge from x to its parent. So this is parent of x. We will say we make a small jump. If the rank of the parent is, let's say, less or equal than 1.9 in the power of rank of x. And we say we have big jump. Let's say less. Yeah. If a rank of the parent is greater or equal than 1.9 per rank of x. Yeah, good enough. Yeah, that's fine. So again, we look on this edge from x to the parent of x in the tree. And if rank of the parent is big enough, we say that this is the big jump. And if the rank of the parent is small, we will say that this is small jump. That's all. Now, let's calculate the number of why it's 1.9. Because I need some number less than 2 actually. I need some number less than 2, but quite close to 2. We'll get to this right now. We'll get to it in a minute. First, let's calculate the number of big jumps. I claim that the number of big jumps in each find operation is about iterated logarithm. So we have m log iterated of n big jumps. Now like this plus this. Why is it true? No, because you start from element x, and each time you have a big jump, you move from element to the element of rank something like that. No, if you have 2 here, you will have exactly something like that. So you start from element that rank 0. Then when you have a big jump, you go to element rank 1. Then you have another big jump. You go to element rank 2, then to rank 4, to rank 16, to rank 2 in power of 16, and so on. So each big jump moves you from element rank x to rank 2 in power of x. So you may make at most iterated logarithms number of jumps. Here I have not 2 but 1.9, but it's not a big deal. If you make 2 big jumps, so if you move from element x and you make 1 big jump, so here you have 2 in power of x, and you might make another big jump, then 2 in power 2 power of x. 1.9. Sorry, my bad. So move here, it's 1.9 in power of x. And you move here, 9.9 in power of 1.9 in power of x. So this will be greater or equal to 2 in power of x. So it's asymptotically the same. If you make 2 big jumps, you move to the vertex with a rank at least 2 in the power of x. And you may have no more than iterated logarithms number of jumps like this. Clear enough? Again, this is the same as here. So iterated logarithm is number of times you may make a logarithm. You may make a logarithm from the given number. And here you make the opposite one. You go from number to the number 2 in power of x. So if you go from right to left here, you start from here, and each time you move to the integer which is 2 in the power of x. So the number of jumps from here to here will be up to iterated logarithm of n. Is it clear enough? Okay, it's actually quite intuitive. So if you look on these big jumps, that if you make a big jump, it means that you go from some very big number. So you move from number x to some number 2 in power of x, and you can't make too many of jumps like this. Even after like 5 operations, you go to the number which is extremely big. Okay, so number of big jumps is at most iterated logarithm for each find operation. So total number will be something like that. That's all. And finally, let's calculate the number of small jumps. To calculate number of small jumps, let's look on some integer, some node x. Yeah. It's big enough to make this proof. Yeah. what else? Let's look at small jumps. Let's look on the number x. No, number x, like, let's look on element x. So, let's look on the edge from the x to its parent. Imagine let's say x is not here, x is somewhere here. So we start find from here, go to element x, then use this edge and go up to the root. Every time, if the x is not the final edge, and we already calculated these final edges. So if this edge is not the final edge, then it means that we will change this pointer to the root. So if we go from here, then we will use path compression and we will change this pointer to here. It means that the pointer is moved to some element with bigger rank. So the rank of the root is strictly bigger than the rank of the of the parent of element x. This is the root. Again, before we make this find, the pointer from x was to this element, the parent of x. And when we make this find, we move this pointer from this element to the root. The root has bigger rank than this element, because ranks are strictly increasing. Each parent has bigger rank than the children. Yes, this edge will become the last edge, but not for this. So it will become the last edge, but then we can like make a union, so this whole this tree will be connected to something else. So these edges will not longer be the last edge, and so on. So last edge is not final. So if the edge is final, that we can then unite this set with another set. So we connect this root to some other root. So these edges will not be final anymore. So it's not like the final point. So if the edge is final, it's not final until the end of the data structure. It's just final by now. Oh. What I was talking about? Oh, again. So when x, if this edge is not the last edge on this path, it means that we will reconnect this x from here to here, and this node have bigger rank than this node. Now let's look on this value. Let's look on this value. I claim that each time you move across this node x, this value will be increasing. So each time, if this x is on your path from this find operation, this value will be increasing each time. Increasing. It's increasing because we move this pointer from here to here, and this element have bigger rank than this element. So this parent was here, and now it's here. So this element have bigger rank, so this value is increasing. Now, how many times can we increase this value until this x became the big jump? So let's take element x. Again. Okay, let's make it slow. Again, what happens? You have element x. It has some pointers here. You have some find operations which access element x. So you have some find operation from here. Each time when this find operation access the node x, you will move the pointer from parent to some another node. So if you go here, then you move the pointer here. Next time, if you go here, you will move pointer even farther. So each time you access node x, you move this pointer up to the root of the 3. So let's calculate the number of such operations after which this jump from x to its parent will become the big jump. 4x. We need to make at most 1.9 in power rank of x operations until the jump from x to parent of x became the big jump. Okay, good enough. So, what I want to say, each time you go through this element x, you move this pointer up to 3. So, when you make 1.9 in the power of rank of x operations like this, the rank of this parent node will be bigger than 1.9 in the power rank, because rank is always increasing. You always move pointer to some node with bigger rank. So after this number of operations, this jump from x to its parent will become a big jump. Because rank of x is constant and rank of its parent is always increasing. That's all. Now let's calculate the total number of operations like this. I want to calculate the sum for all nodes, 1.9 in the power of rank of x. So this will be the total numbers of operations which access all elements. Yeah. So for each element x, we go through this element at most this number of times. So now let's calculate the sum of all these values. How to calculate this sum? No, it's actually quite easy. We will group all nodes by the rank. So let's say we group all nodes by rank. Multiply by 1.9. So let's group all nodes by the rank and calculate the sum for all nodes of the same rank. What we'll have here, how many nodes may have the rank R? So imagine you have the tree, you have several nodes of the same rank. If you have several nodes of the same rank, then for each subtree you have at least 2 in the power of r nodes. And in total you have n nodes, so the number of these elements is no more than n divided by 2 in the power of r. Yes, it's a little bit complicated to get from the first time. You may need to watch it again something later. Maybe it's not the best explanation for this, but I think it's quite clear. But it's not the easiest stuff. Okay, let's go back here. Finally, that's the finish. What we have here? I want to calculate the total number of small jumps. Yeah. Let's look on some node x. We make some small jumps from this vertex x. From vertex x, we will have up to this number of jumps until this jump became a big jump. So the total number of small jumps will be something like that. Now we calculate this sum by regrouping all the summands in the groups of the same of nodes of the same rank. So we take all the nodes of rank R, calculate the number of nodes of this is the number pair of nodes equal to R. So we take all nodes of the same rank, get the number of nodes multiplied by this value. That's all. That's just regrouping of this of elements of this sum. And that's all. And the number of elements which have rank R is up to n divided by sum. N divided 2 in the power of R multiplied by 1.9 power R. This will be n multiplied by this sum. And that's all. And this sum is constant, so this is big O of n. Whew. So here we have last edges, big node, big jumps, and plus n small jumps. So the total number of operations in all these finds will be m log n plus n. And we will assume that m is bigger than n, because it's yeah. So the total time will be up to big O of m log. Yeah. Maybe not the clearest explanation, but okay, that's the first time I explained it in English. That's all. That's why this data structure works in iterated logarithm. And the interesting part, why is it important? Because this function is grows extremely slow, and also all the operations we used are pretty fast. So if you look on the code, then all operations in this course are fast. We just look in the array, go to the link, and so on. So we use very simple operations, and time complexity is slow. So this implementation is actually very fast. It's one of the fastest data structure when you may use, and it's actually almost the constant working time. So like in average you have like 3 operations in this data structure. So it's quite cool. It's really useful. You can use in real contests and so on. Later we will use some. Maybe we'll discuss it. Yeah, we'll discuss it next week in the home task. It can be improved not only to maintain the sets, but also to calculate some functions in the sets. We will discuss it in the home task, I believe. So it can be modified to be able to calculate some different functions on the paths in the trees. So it's very important. So I believe it's all for today. So thank you again for joining me. See you next time.